Now we are doing the third part of the multiple regression story, which is about partial correlations. Let us recall briefly what we did up to now. We have presented our problem of exploring linear dependence between variables as a prediction problem. We have independent variable x1, which we suppose linearly depends of a bunch of variables which are variable x2 up to variable xr, and there is some random error. This part is our prediction. We denote it by such a symbol when we predict x1 based on x2, x3 up to xr. If we do it all in a sample, we add here an estimator sign. The quality of our prediction was measured by R-squared type coefficient, which was defined in the same manner as all of them, which is the difference between total sum of squares minus error sum of squares taken as a percentage of total sum of squares. This can also be written as a model sum of squares divided by the total sum of squares. And it answers the question how much of the total variability of variable x1 is explained by the linear dependence on variables x2 up to xr in the form of linear regression. Now we would like to assess what is the contribution of each particular variable to the overall reduction of error. If we have several variables, then adding each of them to the equation increases r squared somehow. It may not increase it at all if no new information is added, but in most cases it increases r squared somehow, sometimes by much, sometimes by some small amount. And we will want to somehow measure the contribution of each particular variable. So we will concentrate on the pair of variables 1 and 2 so there will be distinguished variables x1, and we will want to measure how much variable x2 adds to the overall regression, provided that we all the time use variables from 3 to r. So what we want to compare, these are those two regressions. Variable x1 calculated based on 2, 3 up to r, and variable x1 calculated based on 3, 4 up to xr. In each of those two cases, we can calculate the error. So we can take the difference between variable x1 and the prediction. This will be our error with the number 1 then 2, 3 up to r. And here we can do the same. Take x1, subtract the prediction, but now based on variables from 3 up to r, and this will be our error of prediction of first variable based on variables from 3 to r. If we have errors, we can calculate sum of squares of those errors. So there will be sum of squares of error 1 based on 2, 3 up to r. This is of course the sum for over all elements of the sample. Error calculated for each element of the sample squared. And the same here. There will be sum of square of errors of prediction of variable 1 based on 3 up to r, which is the sum over all elements of the sample of the squared error calculated at each element of the sample, and here should be definitely I. And now we can again, as previously, compare those two errors. Definitely this error should be bigger, this error should be smaller because we added some additional information. So we define a partial correlation coefficient. Let us do it in red. So the partial correlation coefficient squared between variable 1 and variable 2, provided we have control over variable 3, 4 up to r, equals sum of squares of errors when only control variables are used, minus sum of square of errors when all the variables are used, divided by sum of square of errors, the bigger one, which mean when only controlled variables are used. And this is called squared partial correlation coefficient. Between variables x1 and x2 with control over x3 up to xr. We can look at this thing from a different point of view. We can calculate this coefficient using squared correlation coefficients in those two regressions. So this is how we will do it. Let us recall that in every case the squared correlation coefficient between variable 1 and whatever we have here is calculated in the following way. It is total sum of square minus error sum of squared with the same set of variables divided by the total sum of squares. Therefore, we can somehow determine the error sum of squares using R coefficient and total sum of squares. So we multiply by total sum of squares, then we put everything that has total sum of squares on one side, which means that it is total sum of squares 1 minus R squared with whatever variables we use, and this is the same as the error sum of squares of prediction of variable 1 with whatever variable we use. So now we can take our formula, put it here, maybe a little bit smaller, and now we can use what we determined to put it here and also here. So we have total sum of squares 1 minus R squared 1, and here from 3 to R, minus SST 1 minus R squared from 2 to R, and in the denominator SST 1 minus R squared 1 from 3 to R. And then of course the total sum of squares cancels, and we can introduce some order in the numerator. We will see that those ones will also cancel, and what we get is R squared with all the variables from 2 to R minus R squared with respect to variables from 3 to R, and divided by 1 minus R squared variable 1 with respect to variables from 3 to R. So this is the formula for the partial correlation coefficient based on the total squared correlation coefficients associated to multiple regression. And then there is time to make some interpretation of our new introduced coefficients. So what does it mean that row 1, 2 with control over 3 up to R is 0? So this is 0 if the two errors are equal. So in case when adding variable 2 does not help at all. This may happen even if x2 is correlated highly with x1. This only means that all the information that 2 can provide is already contained in variables x3 and xr. So let us make a note. Value 0 for partial correlation coefficient means that adding variable x2 to the regression function does not improve the quality of our prediction. And let us also note that this may happen even if x2 is correlated with x1. On the other side of the spectrum, there is the case when rho squared between 1 and 2 with control over 3 up to r is 1. This, on the other hand, means that this is 0. So it means that there is no error of prediction in case we use additionally variable 2. So this means that function x1 is just a linear function of those variables. So let us note no error of prediction while using the regression with respect to all the variables from 2 to r. And this means that x1 is a function, a linear function of the rest of the variables. Of x2 up to xr. So this is that. We can look at the partial correlation coefficient in still another way. How to measure partial correlation in different way. In all the statements that I did a moment ago, I used the word control over some variables. So we may think about this control thing in the following manner. We can calculate, as previously, the correlation between variable 1, the multiple regression function between variable 1 and all of control variables. We can calculate the multiple regression function between variable 2 and all of control variables. Then, using the two functions, we can calculate the difference. So subtract from x1 whatever we know from the regression for both variables. So we can think about those differences as removing the influence of variables from 3 to r. So whatever information comes from variables 3 to 1 is removed. 3 to r is removed, both from x1 and x2. So what we get here are, of course, errors of prediction of 1 with the use of 3 up to r, and prediction of 2 with the use of 3 up to r. And then we can ask a question whether these two are correlated linearly. So we can calculate the usual squared correlation coefficient between two variables which are errors. And it turns out that we have, in this way, we have obtained another formula for the same partial correlation coefficient. It says that rho squared between 1 and 2 with control over 3 up to r, it is the same as Pearson correlation coefficient squared between the errors. So this first error variable and the second error variable. And this is Pearson correlation coefficient. Linear correlation coefficient squared. We can, of course, do not square it. We can now, if it is calculated only for two variables, we can forget squaring. So we can now, in a sense, extend our definition, writing such a rho without square, and then it gets a sign. Depending on whether the correlation between errors is positive or negative. So this is some useful point of view because it allows us to generalize the definition. Another thing we would like to know is how we can express this thing or this thing using a covariance matrix, because usually what we get from analysis of our data first is a covariance matrix. And there is a simple formula for that. Again, we write our covariance matrix as a matrix ofCij's, where small Cij is a covariance between xi and xj, and we can take ij belonging to the set of indices from 1 to r. Here it may be useful to introduce another nice and useful matrix. It is a correlation matrix, not a covariance matrix, but correlation matrix. So small pij will be a Pearson correlation coefficient between xy and xj. Of course, the two matrices are related because pij equals cij divided by cii square root cjj square root. So these are related things. And I may write a formula for rho between 1 and say whatever j I want. So whatever is the important variable, while the rest of them are controls. So it means that I stop at the position j minus 1 and then continue from j plus 1 up to r. So this is the correlation coefficient between, partial correlation coefficient between variables x1 and xi with the control over the rest of the variables. And this can be expressed by either covariance matrix, then there is the minus c ij, the upper indices show that these are algebraic complements of the appropriate matrix elements, and here is the square root of C11 Cjj, or using the correlation matrix, there will be minus P1j, again divided by the square root of P11 Pjj, and again these are algebraic complements. In the literature, one can find many ways of visualizing or interpreting partial correlations coefficients. I will present one of them, which is small algebraic illustration, and the other, which is graphic illustration. This graphic illustration has much more restrictions. I mean, it has to be taken with a pinch of salt, but the algebraic illustration is okay. So let us first look at the algebraic interpretation. For simplicity, we will think of free variables, which I will denote to make some associations and make pictures easier by x, y, and z. And what are we going to think of? It will be a partial correlation between x and y with control over z. This is the thing we are going to interpret. Partial correlation between x and y with control over z. So what we do for this thing? Before we start our algebraic considerations, I need some assumptions. The assumptions will be the following: that we have mean values of x, mean values of y, and mean values of z equal to 0, which means that we have moved our point of reference, the origin of our coordinate system, in such a way that the origin is in the point when there are mean values of all the variables, and therefore we can put them to 0. Then, if I look at, say, covariance between x and z, I take 1 over n, sum of results of the multiplication of x and z at point on the sample element omega I, sum over I. There is no so this is like the average, only the average of xz comes into play. There is no part of multiplication of averages because they are 0. But then up to some number, we can look at the covariance as a scalar product. So for us, this will be a scalar product between vectors x and z. The whole question of kernel of the quadratic form here was removed by putting this assumption. So now with this assumption, the covariance is really a positively definite quadratic form or bilinear form, as you would like to look at it. So now we can look at the regressions, pairwise regressions. For example, we can discuss a prediction of x based on z. Since again all mean values are 0, there will be no intercept coefficient, and there will be only b of prediction x based on z multiplied by z. And we know how to calculate it. This is the covariance between x and z divided by the variance x and z. So when I put the formulae here, 1 over n cancels, and what I have as is x I z over omega I divided by here I'm wrong, z over omega I, which is in terms of scalar product between x and z divided by a scalar product between z and z, which is the length of the variable z. Therefore, the map that associates to x, the projection. So I have said a projection. So the map that associates the regression, so the prediction to x, is just a projection, because this is just the scalar product between x and z, and I can write it in the following way: x scalar product between z and the length of z, which is square root of the scalar product between z and z. So I have used part of this b, and the other part of square root I attached to z and divide z by its length. Yeah. So now this is the versor, the length 1 vector in the direction of z, and here I clearly see that the regression is just the projection on the projection of x on the z direction. I have somewhere a picture. Maybe I will just copy this picture. It probably will not be very well visible, but we will see what we can do. This was completely wrong. Sorry. Once more. Copy. It should be copied. This is copied. Okay. I come back to my blackboard. I copy it, say here. Yeah, this is not visible very well. We will try to change colors somehow. Probably this should be made like white. Okay, so something appears. And this should be made white. Yeah, we can see. Okay, so more or less now it is visible. Not perfectly, but visible. So we have, I will correct it a little bit. So we have variable x here and variable y here. I have the directions. This is the this is the direction z, and these are the directions orthogonal to z. And my regressions are just projections of x and y, orthogonal projections on the direction of z. So then the differences between actual variable and the regression are projections on the orthogonal plane. Projections on the orthogonal plane of x and projection of the orthogonal plane of z. And then when I calculate the partial correlation coefficient, which is, according to one of our formulae, it is just, not rho, but r, Pearson correlation coefficient between the differences, actual variable and regression, and the other actual variable and regression, what we see that this is what? This is the scalar product between the projections on the orthogonal direction x, y minus 1z divided by length of each projection. So this is the scalar product between projections divided by the length of each projection. This is the cosine of the angle between of the projections. So we have interpreted in this simple case the partial correlation coefficient. So we look at the correlation between the rests of the variables. Those rests are projections on the orthogonal plane, orthogonal with respect to the variables that we control. In our case, it is one variable, but in general, there may be many of them. So there is the space spanned by the variables that we control. There is the orthogonal plane, then spanned only of the dimension 2. We project our variables orthogonally on this complement, and we take a correlation between those projections. And this is a very well interpretation, algebraic interpretation. The graphic interpretation is a little bit, it is not that good. For two variables only, it works much better. So let us write now graphic interpretation. So if I have two variables only, and when I standardize those variables, so two variables, say variable s, no, it's too thin, variable s and variable t, and they are standardized, which means that they have mean values equal to 0, and we have variances equal to 1. We can think about each of the variable as the circle of the same diameter. Did I manage to make them of the same diameter? Almost. So such a picture as written here, as this one, represents uncorrelated variables. Then I need them multiplied. I will need 2 of these, and I will also need 2 of these. Yeah. So these are totally uncorrelated variables. These are a little bit correlated variables, and those two are totally correlated variables. So in case of two variables standardized, one can show that there is the following there are the following relations. If we say predict S based on T, we again have only B as T times T, because mean values are 0. And one can show that then the variance of S is equal the variance of the prediction plus the variance of error of S based on T. No, because prediction and error are not correlated. And then we can show that we can show also that rho square of S T, which is of course variance of S minus variance of error divided by variance of S. We remember that variance of S is 1. So as a matter of fact, we have 1 minus variance of error. And variance of error, then then is 1 minus rho square S T. I again used rho instead of r. I'm very sorry. It should be r squared, and it should be r squared S T. So in case of the correlated variables, I may think in the following manner. So if this is the square of S, then here we have r square of ST, and this thing, only this thing, is then the variance of error. And this is very nice graphic interpretation, and in case of two variables everything works. So this is something we can imagine, and there is no untrue conclusion that we can draw from such pictures. However, if there are more variables than two, then this graphic interpretation starts to look in the following way. We need 3 variables in general position. So again, standardized, and maybe this should be a little bit lighter. Yeah, are they the same? Almost. And the red one, again, almost. So we have now variables, say S, T, and U. And we can write our surfaces. We can denote them by D. No, it isn't visible. It should be white. So this will be D, this will be B, this will be C, this will be A, this will be E. And there are some relations that we can write here. So again, for 2 variables, r squared between, say, S and T will be S and T will be D plus B. No, B plus C. So this will be B plus C. The same we can write for R squared, say S U, this will be A plus C, and R squared U T, it will be E plus C. And as for now, it works perfectly because there are only two variable things. However, I can start to think that maybe R squared is SUT. It will be just A plus C plus B, A plus C plus B. So everything of S then that I can explain by T and U. Yeah, and this is very well because then I can write those correlations coefficients, partial correlations coefficients between, say, S and T with control over U. This will be B divided by B plus D. And there is, I mean, this is not that easy now because there is some scaling here, as you can see. You might think, okay, if I remove the influence of U, this partial correlation coefficient should be illustrated only by B. It is, but up to some scale. And of course, the same happens. When we write partial correlation coefficient between S and U with T, which is removed, and this is it should be what? It should be A divided by A plus D. So this works, but we may be tempted then to look, okay, so what happens if some of the variables are not correlated? For example, say the picture looks the following. Here I have one variable, sorry, wrong color. So here I have one variable, here I have the second variable, and here I have the third variable. And again, it is not circular. Let me draw it a little bit better. This is circular, okay? So now it looks as if there shouldn't be partial correlation between this variable and this variable, because there is no this intercept, and this is the place when our graphic description is completely wrong. So one may visualize things a little bit like that, but drawing too much conclusion, it is a wrong idea. Don't do that. We will probably rather stick with algebraic interpretation, which is valid, which is presented here in 3 dimension, but it is valid for any dimension and correct for any dimension. Okay, so this is the lecture finished. The next lecture will appear next week and will be about the procedures of selecting variables to multiple regression in case when we have many variables available, but we do not want to have too complicated models. So how to choose between the big set, in between big number of variables, the set which is small but still efficient.